Okay. Um, so so yeah, what are we talking about today? We're talking about what organizational principles in non-equilibrium systems, we could say, kind of at the most generic level. So this is a project that Alec and I have been working on for some number of days, uh, in the hundreds, I think, but maybe not in the thousands at this point, uh, low hundreds. And it's it's essentially addressing what is some century old question in non-equilibrium thermo about how do we generically describe the behavior of systems when they're driven away from equilibrium, open systems. And a way to approach doing that would be to a really elegant way would be to find an organizational principle because we love them, right? As physicists, we just love an organizational principle. It's something that feels so beautiful when you can find like one concept that then just explains so many things at like the highest level, right? I think probably a lot of us when we first saw something like this, it was maybe like a light bulb moment of like, oh, I'm a physicist because I appreciate this thing so much that that must be my calling. Like a couple of these that we see, I think typically for most people you see these in undergrad. Uh, is like for closed systems, the principle of least action. So you find that you have a Hamiltonian system and you fix the start point, you fix the end point in phase space, and then you can just like have one thing that describes like how it's going to go from one thing to the other, one principle. Of course, not all systems are closed systems that we deal with. In fact, essentially no systems we deal with are closed systems. It's much more common that a system of interest is interacting with the environment, but luckily we have one for that too, right? As long as the system is in equilibrium with its environment, we know that we can predict how the system is going to organize itself, right? It's going to organize itself to maximize the entropy. It's going to dissipate nothing. Okay, that's cool. What happens for non-equilibrium systems? Uh, all of a sudden, that instantly gets way worse, right? We know that there's some entropy production greater than zero. It's non-equilibrium. But how much is it, right? Is it a billion? Is it one? Is it 50? What does the system want to do when it's driven out of equilibrium? This is a question that I think people have wondered about for a long time. And maybe it's an impossible question, right? Whenever you're defining something by what it's not, you're opening up a real can of worms. But when you have a dissipative system, you have cases where you have something like a lazy river uh, where a river is kind of slowly dissipating its energy as it kind of winds its way down into the ocean, or you can have like a raging forest fire, which is a very quick, kind of violent approach to equilibrium. And it's the question is like, how do you know which of these happens? Like, what is the natural state? What does nature want to do? And is it possible to even know? In the literature, I think it's fair to say that there are people who kind of believe both of these different hypotheses. There's what we're calling MinEp, which is the idea that a system, when it's driven away from equilibrium, tries to dissipate as little entropy as possible, and one when it's driven away from equilibrium, it tries to dissipate as much as possible. And there are people on both sides of this, which feels a bit wild when you think about them as total opposites. But a lot of that has to do with, I think, definitional stuff more than anything. It has to do with what setting you're interested in, how you frame the problem. Um, and if we try to strip that away and go back to hopefully with the original setting of the problem, we'll see how far we can get. And that's what I want to do today. So what we want to do is describe a framework, a class of models, and then also a clear definition given this framework in the class of models for what we're going to talk about, what we mean by min and max entropy production, and to try to do this in the most clear way possible. Then we're going to look at the kind of implications of what these kind of clear definitions are in the framework, and then we're just going to simply just roll from there, right?
Sorry, can I ask a question?
Yeah.
So you have these two examples of minep and maxep. Maxep. Um, there's the river and the forest fire. And I guess I'm wondering, isn't the fact that both of these exist, doesn't that indicate that both happen in nature with some frequency? I mean, if the question is, does one or the other tend to happen? Um, the answer is kind of yes to both.
Yeah. Yeah, I think that's totally fair. Yeah, both happen. Of course, this is the thing that you run into when you decide that things are non-equilibrium, right? Is there's a lot of different types of non-equilibrium phenomenon. So
Though,
the question, and you could make this similar to the question of least action, right? Which is like given some drive, which in that case the drive is setting the start and ending point in phase space. What does the system prefer to do? So given two alternative paths, which is chosen?
though I should point out, is something like a fire really max up, or I mean the maximum entropy path would be basically for everything to instantly atomize, and it would be for the the forest to explode, and turn into carbon nearly instantly. That would be maximum entropy production, would it not?
Yeah, I think that that's actually something we're going to run into in a number of slides, in fact. The in some ways the definition, even like the idea of maximum entry production, is somewhat ill-defined in a lot of frameworks because the question of like how much entropy you know, you can dissipate is actually turns out that's undefined, I would say, especially in our framework, it will be.
So maybe the organizing principle we're looking for is when is entropy production minimized or maximized and why?
Yeah. Or maybe even better, ignore the idea of minimum and maximum and say, given a particular drive, what can we say about how the system is going to respond? Maybe it does not actually that helpful to call it min or max because there's actually a lot of middle ground in between. And so
Yeah.
yeah, so it's kind of like is there some balance going on here that involves more than just entropy? I think that's likely. In fact, this is maybe, yeah, a good time to pause before we kind of move into the mathy stuff. Are there other thoughts or questions before moving on?
Uh, I have maybe one other, but feel free to either ignore or address this later. Um, I'm kind of wondering like what made either of these tempting targets for an organizational principle? Was it just that there weren't many quantifiers of non-equilibrium systems? Because like there are infinitely many things one could come up with, and it would be uh, kind of absurd to say a random quantifier that I come up with will be minimized or maximized like without good reason. So I'm wondering if there's like a strongman argument for each case.
Yeah, so for the minimum, I would say the minimum is easier, I think, to take on as a target because you think, okay, I have interacting system that's allowed to go to equilibrium. It goes to equilibrium. And then I start to push it out of equilibrium, right? So it's like going from the zero dissipation state to some drive.
Mhm.
And in the limit of like weak driving, it stays close to equilibrium. That's basically the original, I would say the original Prigogine stuff is in that regime in a way, which is
Right.
like you start from equilibrium, you say what happens if we drive away from that. And there's idea that locally there's some pressure back there, and then you extrapolate to say, oh, it's always trying to get towards equilibrium. It wants to
Mm.
be as close to equilibrium as possible.
For clarity, MinEp is true in equilibrium because the equilibrium state produces zero entropy, which
Yeah,
is the minimum it can.
right. I guess we should also maybe get towards the definitions of these to talk more concretely about it.
It's true.
But at
Uh,
like an abstract level, zero entropy production as like an attractor because that's the equilibrium state makes sense to me.
I
so
think,
that's oh, go
sorry,
ahead.
I think in terms of motivation, there's this story that people tell about life as, harvesting free energy and using it for its purposes, right? And when you think of like non-equilibrium systems as living systems and the patterns that we see to of those systems to store energy, use energy, you come to different or you tell different stories. I think the Minep or sorry, the Maxep community is more coming from the ecological perspective. Um, I think that idea has been more embraced in ecological science communities or complex systems communities. Um, and I think the idea is there is, okay, what is a competitive organism? Well, a competitive organism is one which can expend and use energy more efficiently or more rapidly and therefore outcompete its other organisms. But on the flip side, if you waste all your energy, um, you are not an efficient organism. So maybe that leads you to minute. Am I just making a word salad here, or does this make some sense?
I think I think it makes sense as like a qualitative overarching story and a reason to point to why there would be why people would think that both of these things are reasonable.
I,
Uh,
I think in terms of motivation, the hope for a lot of these principles was to connect physics to living systems, to build a bridge from, basic physical law to, biology essentially. And that's been a very difficult connection to make. But I think these organizational principles draw on an intuition that there should be some rule of the universe that leads to life, for instance.
I have a question now, which might be best answered by letting you get on with your talk, but it's that if I have some rate equation that is describing my system's dynamics and it starts out of equilibrium and it moves to equilibrium, the rates are what decides the entropy production rate, right? So
yeah.
why would what's the difference between, oh, the rates just decide this and somehow there's this universal principle?
Yeah, yeah. So this will be, I think, hopefully this is number one and two here. This is basically carefully defining what we mean. And yeah, we're totally doing rate equations. So I think that will become clear in a second. Uh, and maybe just to wrap up this idea about why there's a belief that maybe max EP is something reasonable to do, is that you will find that if you, for example, start a system so that it's sharply uh, peaked on a state that locally has low entry production, that the dynamics of the system will evolve towards the states that have higher entry production. Like if you're in such a state, and then that might make you think like, oh, the system is maximizing its entropy production. I think a lot of the arguments I've seen are based around something like that, that there are regimes in which states that locally produce a lot of entropy are attractors given a particular initial distribution. But and that will be more clear, I think, as we go through and kind of write out some math. Uh, is that Are we ready to move on? What do you guys think?
Yeah.
Great. Okay. So I think don't need to get too in the weeds here. This is a pretty standard approach that we're taking here. We're using the kind of really normal stochastic thermodynamics approach. We have a system, it's interacting with some number of baths. It also has a control that's allowed to go work on it deterministically. And in this way, you define entropy production as the entropy that's being generated in all these baths, plus the change in entropy of the system. With this definition, you get your Crookes fluctuation theorem, and you can build a lot of stochastic thermo off of this. Okay. Now, the model class we're going to use here, because this, of course, stochastic thermo applies like broader than just discrete state rate equations, but we're going to use this continuous time Markov chain approach, where we have a set of discrete states S with occupation probabilities and a transition rate matrix R, which tells you the transition rates from S to S prime. So these CTMCs obey rate equation dynamics. in the usual way here, where the time derivative of each state is just summing over all the different transitions from S prime to S. And entropy produced in the environment associated with these transitions is just the log of the ratio of the forward and reverse transitions.
So that's the entropy flow into the environment, which can be heat, chemical potential. Oh, yeah, you have it written in that white arrow above.
Yeah,
The sum of the
this
heats
guy
and
up here.
chemical
Yeah.
potentials and all that.
Hmm. And the oh, okay, never mind. I take it back.
Those who are into time symmetry will feel like I'm cheating you here, but we'll get into that later. So um, we have here A, B, C, like a three-state system, and basically these arrows are indicating kind of the strength of the transitions, right? This is a pretty normal model. So let's just sum up. We've got our CTMCs, which have their particular time derivatives. We have
Okay,
our
sorry, I guess
definition. Yeah, go ahead.
sorry, I do have a question. So the rates are fixed. There's no like work like driving, is that right?
That's correct. Yeah. Uh, um, yeah, with these definitions here, we end up with, we can just take basically, you write out the exact thing for the sum of those two terms. I talked about the entropy production in the environment and the change in entropy of the system. You take the time derivative and you get this sigma of R and P. This is going to be our quantity that we care about. This is the entropy production rate. So it is a function of R, a fixed rate matrix, and P, a particular distribution over the discrete states.
So the
And
result of these, or sorry, the cause of these rate matrices is, basically thermal fluctuations and continuous time that can come from chemical reservoirs, heat baths that drive potential asymmetries and violations of detailed balance, right?
yeah, yep.
So there's no external driving outside of like maybe the influence of a battery or a temperature gradient.
Yeah, our framework is very much instantaneous time. So there's not really an option for there to be any kind of time-dependent control here, I would say. It's a good way of thinking about that. And I'll make that explicit in a slide or two. Just for example, here we can see that we have cases where you can have zero entropy production, an equilibrium system where everything is kind of flowing in and out at the same rates, or you can have some kind of non-equilibrium steady state here where there's a net flow through the system. There is entropy production, even though the distribution over the states isn't changing. So we've set up our framework of stochastic thermo. We've talked about, we're going to use CTMCs. We've talked about the definition of entropy production rate, but we haven't given a clear definition of what we mean by min and max EP in our setting. So let's approach that now. The important quantity here, this entropy production rate, is a function, like we're saying, of R, which, like Alec was saying, this is your bath interactions, your control drives, batteries, and then you have P, which we're going to say is kind of the response variable. This is the distribution, the thing that's allowed we're going to kind of optimize over. So we're going to always take R as fixed, and we're going to allow P to float. But we're going to pick one particular special distribution and call that the natural response of the system. So that's the special state distribution that has a zero time derivative for all states, and that's called the NES, the non-equilibrium steady state typically. And this is very in keeping with the foundational work by Prigogine. This is how they defined this, was that the natural response of a system was defined by a steady state, zero fluxes between states. And so we define this NES, which is basically the state distribution for which all time derivatives are zero. And you just plug that into this guy and we end up with sigma pi, the steady state entropy production.
And so as the kind of rate equation setting, this assumes effectively that the like graph, if you think of like the graph of rates between nodes, between states, that thing is ergodic effectively. Otherwise, you would have multiple solutions, right?
Yeah. This is assuming there's only a unique steady state,
Mhm.
a single one.
It's my
And
impression if it's fully connected, it's pretty likely to be ergodic.
Yeah. Um, yeah, in fact, I think ergodic is too strong of a claim. I think if there's a single component
That's the part of ergodicity that I had in mind. If it's a single component, then there's a single
Right.
should be a single steady state.
In Markov chains, you can have irreversibility even if you're fully connected, which would mean like, you can split off into separate subcomponents. But because of detailed balance here, uh, I think, that sort of irreversibility would lead to infinite entropy production. So, anyways, just some context for the sort of rate or dynamics, you know, thermodynamic rate equations typically realize.
Right. Okay, yeah. So with all this background, now we can just be very pedantic and explain exactly what we mean by min EP and exactly what we mean by max ep, which is here, min EP is when sigma pi is the same as the entropy production when you put in the distribution that minimizes entropy production, right? That's what this is over here, argument over P, a sigma of R and P. We'll call this thing the MEPS, the minimum entropy production state or minimum entropy producing state. And this is basically supposed to be an analogy of the NES, the non-equilibrium steady state. Both of these are actually state distributions, but typically people refer to them just as NES. So we're going to refer to this just as MEPS.
I don't quite understand what you're minimizing over. Is the possible initial state of your system or the final state of your system or something else?
Yeah.
Well,
So
time trace.
yeah. This is why these notes are down here. So these are two important notes that really like pin down exactly what we're looking at, which is that one, everything we're looking at here is passive. Okay, so R is fixed, but it's not just passive, it's also instantaneous. So we're looking at entropy reduction rate at like an instant fixed frozen in time, not an integrated entropy production over a state change. So we are able to associate it's not a sequence of states that the system is going through. It's one distribution. And we want to know at right now what's the rate of entropy production, as if we just froze time with no interest of what's going to happen later. So this way we kind
What
of
are you holding contact constant? Like
the rate matrix.
the initial condition, the step previous time step is held constant?
The rate matrix and the instantaneous distribution over states, P.
So the rate is constant, P is variable. And there is no previous time step because P is basically effectively the same over an infinitesimal time step, which is what you evaluate to calculate the entropy production. Does that make sense?
No.
Yeah, there is
Not
like
yet.
okay, so there's no computation. This is like I think one of the important things to point out is there's no computation here. It's not like the distribution starts in one distribution, ends in a different distribution, because we're looking instantaneously at one point in time. So if you one way to maybe imagine this is it's like if we just have a fixed R and we start at time t equals 0 with an initial state, but then we never go past t equals 0. We're just looking at what's the kind of instantaneous entropy production at that instant without thinking about any relaxation to steady state, any kind of transients that might be visited in between.
So it's essentially, I could think of it as what's the maximum entropy I could get right now? What distribution as an initial condition I could get, right? I can always think of it as the initial condition.
I think you can always think about it as the initial condition as long as you realize we're only measuring right then and not in terms of what happens as you relax to steady state and integrating over that whole thing. We're not worrying about that at all because it's possible you could have a very low entry producing initial state that for some reason triggers like a very weird transient that's very highly dissipated later. And we're not including any of that part of it. It's just like we'll sweep over all possible initial distributions and think about what that instantaneous rate is.
Okay. But so then if I start with a different distribution, then there's no way I could get to the min-ep distribution because we're only talking about instantaneous, right? Like if I hand you a real system, it's going to have some R and it's going to have some P, and that P won't be the P that gives you the min-ep.
Yeah,
probably.
yeah.
But
So
as it
the
evolves, it will relax to equilibrium, the non-equilibrium steady state, right? And that
Yes,
non-equilibrium steady state, the question is that close to the min-up distribution? Is it close to the max-up distribution?
I see.
Does that make sense? Yeah.
Yeah, thanks.
Yeah, so like if we look at our definition of entropy production rate here, right, we don't have any time dependence here at all. It's dependent just on some distribution over states and a fixed rate matrix. And so the idea here is we're ignoring time, whether what states can visit, like what distributions can visit other distributions, and just saying like, what if we optimize this distribution as a free parameter? We pick one of them, which is special, which is this non-equilibrium steady state, because we know that if you start there, you're just going to stay there. And we compare it to all the possible other distributions we could do. And we want to know how close some of this special one, like Alec was just saying, is the min one is to what happens with the steady state and what would happen, for example, if you wanted to argmax instead of argmin over all possible distributions, you get the maximum entropy producing state. How similar is this steady state to that one? Yeah, and this is I feel like there's like they're not unrelated questions, but they are separate questions. This versus what happens if you kind of integrate starting at a steady initial state, going to the steady state, integrate over that time. Um, and just to kind of reiterate that point, our framework here is just kind of passive because R is fixed. It's instantaneous because there's no time is not allowed to move at all. It's not like an active system where you're doing a computation. It's not integrated over time in that way, right? So there's no task, and relaxation to Ness is not an important thing that we're interested in here. As a cartoon, we could say that out of like we have lots of different rate matrices that we could sample, and each one of these rate matrices has like a maximum entropy producing state, a minimum entropy producing state, and a steady state. And we're interested in like what does this Venn diagram look like between these three different cases? So generically, it might be the case that the minimum and the maximum entropy production are the same. Okay, that would be, I guess, kind of pathological, where there's only one entropy production allowed. But theoretically, maybe that's possible. So there's an overlap here. But more generically, you can imagine the steady state might sometimes be the same as the maximum. It might sometimes be the same as the minimum. And it might even be, if there's only one entropy production, it has to overlap this guy. But it could also be its own thing, right, with no overlap. And then given that, the kind of three different hypotheses we could look at is min EP, which is essentially, let's get rid of this overlap in the middle. That's such a pathological example. We don't need to worry about it. We've done something real weird if we're ending up a situation where there's only one entropy production. It's not really a very meaningful investigation. So assuming these two things are just disjoint, then the Ness overlapping completely with the minimum entropy production state, this is the concept of min-ep. The concept of max-ep would be the Ness overlapping with the maximum entropy producing state. And then maybe you have mid where it's like mostly minimum and only a little bit of maximum or something like that. Okay, so to get the first thing out of the way, there actually is no maximum entropy production in this stochastic thermone the way we've defined it here. This first term, we can break the entropy production into two terms. One of them is a time derivative of this delta S environment. And unless we have these unidirectional transitions, which aren't really thermodynamically consistent, then this thing is always going to be finite. On the other hand, this guy over here will diverge when a state has a zero probability because you have this log p. And so basically by going to the edges of the simplex, you end up with these kind of instantaneously diverging entropy production rates. So at least in our framework, it's not even a well-defined thing to talk about the maximum entropy producing state. So we're going to separate it off its own thing. And it's certainly not the typical case that it's the steady state because typically things do not dissipate infinitely. So really our main question is how close is the steady state to the MEP state?
Max-up would pose something like an ultraviolet paradox if it were true, because it would mean the steady state produces infinite entropy constantly.
Yeah, which is not a good idea, nor consistent with observation.
Sorry, could you just go back to that? I want to make sure I'm understanding the 2 points there. So I think I understand the point on the right, which is if the probability is 0, log probability is going to negative infinity. So that guy's blowing up. I think I'm not understanding the point of the time derivative of the expected um, change in entropy of the environment. Um, you're just saying that it is okay. Sorry, I thought you were putting these two in tension, but it's just like these are two things that are true.
Two things that are true. Yeah.
Okay,
Yeah, and it's like maybe these two are opposite signs, and somehow the divergence here is offset by this one, but that's actually not possible because this thing is finite. Is that
right. So one point I can take from this is that um, if we assume bidirectional transitions and we allow for uh, distributions that are at like edges or vertices of simplices, then there's no max because this thing has like it can be infinite.
yeah.
Okay. Okay. Thanks.
Okay, so that's maybe disappointing, but we can make a bit more progress here if we look at the minimum entropy projection. So doing basically the usual thing, you could use a method of Lagrange multipliers to impose a probability normalization on sigma, minimize by taking derivatives, algebra, and what you end up with is a condition, right? You end up with an equation for the P that minimizes the entropy production, and we call that thing ebb sub r, and its time derivative follows this interesting relation here. And it breaks into two terms that are easily interpreted. The first one is the entropy production like conditioned on being in a particular state S. It's kind of like local entropy production from state S. And the other one is the average of this thing over all states. And what we see here is that the minimum entropy production distribution, the MEPS, for a state S that's a high dissipation state, higher than average, actually it collects uh, probability on those states. And if it's a low dissipation state, it actually sheds off probability on those states, which is exactly what you might expect for something that has a minimum entropy, right? Both of those moves take you towards higher entropy producing distributions.
Which must be the case if you're at minimum, you can only go up.
Yeah.
I like also that this is the derivative of the surprisal of as opposed to just like the derivative of the probability.
Yeah, yeah, you can write it in terms of the derivative of the probability, which we do use for something, but in fact, this is a lot more a nicer, more interpretable equation, I think, like this. It works out really nicely. So this is the first 2 points. The third one is that you can now see there's at least one case where we're sure that this will be a steady state, right? If this right-hand side of this is 0, that means that the time derivative for all S of MR is 0, and it's a steady state. So that's the case where the local entropy production, kind of conditioned on being in each state, is the same as the average over all states. So these are these kind of high entropy production symmetric setup. You're going to end up where the minimum entropy production, MEPS, is exactly the same as the steady state. And the final benefit of this is it gives us a nice iterative algorithm in order to get to M sub R for any rate matrix. So we can basically plug in a rate matrix, evolve in this computational time tau for which the MEPS is the steady state. It's kind of an altered form of the time derivative. And in fact, just by iterating through this thing, we've got a hammer now. We can just hammer on rate matrices and it spits out the associated minimum entropy production distribution. So after looking at this thing, we have somewhat of a nuanced picture here, which is that typically this thing is not a steady state, right? Except for in a very specific situation. So pi and Ness and MEPS, not the same thing, but there are cases where they overlap. So we know it's possible for them to be the same thing. And that means, in some ways, you could say that MinEp isn't true, right? We can't say that it's definitely true that systems minimize their entropy production because there exist states that are typically lower than the steady state in entropy production. So how does this relate to Prigoghine's Ness and MEPS result from quite a while ago? So the setup there is this linear response regime where you have these forces, these fluxes, in entropy production that's the sum over a product of these guys. And a couple of assumptions going in here. One is that you're in the linear response regime where the fluxes and the forces are related linearly. and also that you have the Onsager reciprocal relations, that these proportionality constants are symmetric. If you just plug this in a few lines of algebra, you can show that minimizing sigma with respect to the forces x implies that all the fluxes vanish. And that's interpreted as uh, enforcing minimum entropy also enforces a steady state. Um, Now, in our case, we didn't find that, and we didn't find that even though we can essentially map each one of those steps onto something we've done. So we also have forces here between pairs of states, right? That's the log of uh, the probability to be in that state times transition rates. We have fluxes between states, the probability flow from S to S prime, and we have an EPR that we can write as a sum over pairs of states of a product of these guys. Um, okay. However, each one of these things is subtly different from what is assumed in the Prigogine setup. So for one, instead of just optimizing the free forces x, we're optimizing over p, which isn't totally free because the probabilities are normalized, right? They depend on each other somehow. On top of that, our fluxes are not linear functions of x. If we were to write this in terms of a function of x, in fact, there'd be exponentials in here, right? You can imagine there is some kind of small force regime in which it's linear, but that's typically not the case. Um, the EPR, yeah, it does work out to be this product thing, but the conclusion here that vanishing fluxes, if j equals 0 is a steady state, is actually not the case for us, right? We can have non-zero flow from S to S prime in a steady state because it just needs to be compensated by some incoming flow into S from other states. So because of all these reasons, it's not too surprising that what we find is in violation of the kind of foundational Prigogine work. Um, so with that in mind, we can just kind of state our predictions, which is, yeah, we expect NES and MEPS to be not the same typically, except for the cases of equilibrium, trivially because in equilibrium there's zero entropy production, so that has to be the minimum. And also for these highly symmetric systems where locally the entropy production from each state is the same as the average. So,
So,
yeah.
just to interpret this symmetry claim, this means that if there exists a permutation on the states that leaves the architecture of the rate equations invariant, therefore that rate uh, equation will lead to the minep state in equilibrium or in steady state. Am
Yeah.
I, yes.
Yeah, I think that's a good interpretation of it.
One way of interpreting it, I suppose.
So let's take a look at a simple toy model where these things are kind of easy to just calculate exactly. We're going to have it's a three-state model here where the rates are determined by Arrhenius equations. We got three terms in here, three energy terms essentially, right? There's the energy scale of the state. There's a barrier between any two S and S prime. And then there's something that we're going to be able to put in by hand, which is a non-equilibrium driving force from S to S prime. And we'll determine um, the thermodynamics by local detailed balance, where Q from S to S prime is going to be the same as minus Q from S prime to S. So in the three-state model here, you can imagine, let's start at state A. You can see kind of like you get these big rates down to B with lower rates from B to A. So if we're in equilibrium, that's implying A is like a higher energy state than B. And you can do the same argument from B to C. So in an equilibrium system, then you'd be quite unlikely to go from C to A, right? Because you're jumping from this low energy state to this high energy state. But in fact, by adding this non-equilibrium driving term, we're able to artificially pump that up and support a non-equilibrium steady state and drive this thing out of equilibrium. Some cases that we should expect NES and MEPS to be the same is one, the equilibrium case. Okay, so that's if we didn't have any non-equilibrium driving and this Q was actually just, I think, minus 2 delta E because each one of these is delta E. And another one is the highly symmetric case. So if we artificially pumped transition from C to A such that kind of it had exactly the same, like the rate from C to A and A to C is the same as B to C and C to B, then we should have basically just a three-way rotational symmetry here. And again, each state should be kind of entropically the same as each other state, and we should end up with MES equals MEPS. And that's exactly what we find. So the equilibrium case and the uniform cycle are cases where the non-equilibrium steady state and the minimum entropy producing state are exactly the same when we calculate it out. And what these plots show is essentially starting in either the uniform state or the minimum entry production state and seeing what happens over time. So in the case of very strong driving, you can see we start at uniform and this thing over time goes to the steady state as expected. But we can also start in the minimum entropy state, which has lower dissipation. And as you evolve, the dissipation increases as it goes to the steady state. So here's an explicit case of min-ep violation in the case of this very strong pumping to push you out of equilibrium. So as you weaken the pump, you can see that these things become more similar. Here, they're all three exactly the same because uniform distribution in the steady state are exactly the same. And that also is the minimum. Over here, they look close, but in fact, if you zoomed in, you'd see that there's differences here. So this is just the scale is condensed. And then over here in equilibrium, what you see is that the uniform distribution is highly dissipative, and it's not the same as the equilibrium distribution. But in fact, the equilibrium distribution and the ness are the same exactly down here. So we can look at a picture that instead of just looking at a few cases, we'll just sweep over all the different pump strengths. And what you see, of course, is a regime over here where the ness and the MEPS are diverging from each other. They're significantly different at the high pump strengths. And as you go down to this symmetry case right here, you have they kind of come towards each other, and you actually see here's a little close-up of looking at the difference between ness and MEPS and uniform and MEPS. And what you'll see there is like these guys are all going down to exactly 0 right here because basically because they're all three exactly the same thing. So the distance from the minimum entropy production is 0 for uniform and also for the ness. Okay. Then down here at these kind of pump strengths over this way, it looks again like maybe the ness has converged to be the same thing as the MEPS, but in fact that's not true. So if we look again at the zoom, you can see that there's another place down here where it hits 0. That's our equilibrium case. But then as you continue on, it diverges off again. So this model is kind of explaining exactly what we would have expected from that result of what we expected for the minimum entry producing state. Any questions before we move on to the big systems?
Just noting it's a cool example where like just visually it's like, oh, these things do in this example feel pretty close. It's understanding why things can be misleading.
Yeah.
I think it's suggestive that you definitely have violation, a very clear violation on the right-hand side of the middle dotted line, but then they're very close to MINEP or MEPS on the left-hand side, deceptively close.
Yeah. And I think that what essentially the rest of what I'm going to talk about are examples, simulations, test cases. And in these test cases, you're going to consistently see this pattern that MEPS and NES are not the same thing, but they're surprisingly close. And you might even say deceptively close, that if you were, for example, going to have like a qualitative guess or phenomenological guess, it would be a totally reasonable thing to conclude that they are the same. So that is actually probably really well seen if we think about larger systems. So we're going to introduce a figure of merit, which is basically the additional entry production above the minimum here as a percent of the entry production, the minimum entry production. So if this thing is 1, that means you're double the minimum. If this thing is 0.1, that means you're 10% above the minimum. And we're going to take the same model, that 3-state model, essentially, with some pump transitions, and we're just going to blow it up to n states with n pumps that are going to just all be kind of uniformly sampling energies, uniformly sampling pumps. And what you see is for the far left over here, which is very small systems, there's this big diversity of behavior. We're going to plot things that are chosen randomly, uniformly over the simplex. We're going to do things that are uniform, meaning that it's a good 1 over the number of states is the state. And then we're going to look at the ness. And in each case, we're going to quantify their distance from the minimum. And while there's a lot of diversity here, as n increases, these things converge into these really, really tight groups that are well separated. And you can see there's like a hierarchy here where The random states are dissipating more significantly than the minimum. The uniform is less, but still pretty close to that. And then the nest is like another order of magnitude down in terms of closeness to the MEPS. And in fact, we can see, like, let's just track nest for a second, because that's what we really care about, right? These are kind of nice for comparison, but in fact, this is our special distribution that characterizes the response of the system. And what you find is this non-monotonic kind of increase for some number of n, and then this is tracking the average here, this dot. And then starts to go down, down, and down as you increase system size. And so while here at this 27 state um, system, maybe you're producing 50% more than the minimum possible. Here you're only producing, less than 10% more, right? So so there's some interesting behavior that happens here as the systems are getting larger, which is it becomes harder and harder to observe violations of MEPS as the system size increases. Violations of, wait, not MEPS, what is it? Min-EP,
Mini.
minimum entry production,
Yeah.
min-EP.
Minute.
Um,
Oh,
so
sorry, can we go back to the slide
yeah,
before? I think you kind of dismissed the random and uniform distributions as just points of comparison, but I think there is something dynamical we can take from this, which is to say, okay, let's say you have a, rate equation, and if you just plot down some distribution in it, whether it's maybe you just start totally uniform or you just pick a point on the simplex, it seems to me that what this is saying is, in general, you're going to find that in relaxing to the steady state, you approach a distribution that produces less entropy than you started with, which I think is suggestive of
yeah,
some sort of adaptation, that the free parameter is somehow, quote, adapting to the rate or the dynamics of the system.
yeah, that's actually a really good point, right? There is more to analyze here. And specifically, like one thing you can say is like um, if you just pick a state out of a hat to start, you're almost always going to see a reduction in entry production as the system evolves. Because almost every state is, like, for example, choosing uniform randomly over the simplex, right? All these guys, all these states are all way up here. It's only a very special, like the nest is a very special set of states that are significantly lower than almost every other state. And then the MEPS is an even special state that's lower than this. But typically, what you find is that starting in just some state out of a hat, as the system evolves, it will reduce its entry production, which could really explain why it's very common to see the idea that min-EP is true. Because when you let states evolve from initial conditions that aren't necessarily these very specific ones that we've found here numerically, then you're going to almost expect every single time that as it evolves, it goes to a lower entry production state.
Jeremy England and I forget the other uh, person he worked with on this paper had a result that echoes this, where they were driving a spin glass with different signals. And um, they would see, okay, there's a persistent amount of work absorption, which is basically a measure of entropy production for different driving signals. And when they would change the driving signal, they would see that there was suddenly a spike in the entropy production, but that the system would then relax to the signal, the driving signal. Somehow the spin glass was, quote, adapting to the signal and
Yeah,
producing less entropy as a result.
yeah, I think this explains that pretty well. And you also see this in um actual experiments where people have like boxes of sand of different grain size. This is a pretty common thing. Like that's an interesting situation where you can compress this thing many times in the same way, different ways, and you see exactly the same kind of thing where it tends to evolve to states that are lower entropy. Yeah.
Yeah. So each of those perturbations, either in the England case or in the sandbox case, like it's like resetting the rates or something, and then it's unlikely to be the steady state, so you get the decrease. It's the minimal rattling.
Right. Right. Yeah. That's the principle that England likes is least rattling or most rattling.
I think it's least
Minimal
rattling.
rattling, I thought.
Yeah,
I don't
I
Minimal
think it's
rattling.
minimal rattling. Um, okay, so this system is actually not that big. It only goes up to 700 states, which of course is a lot of transitions, but we can just keep it going. So here we're going up to 20,000 states. Um, and basically, if you follow this line, I'm just tracing this line for a bunch of different experiments over different strengths of the pump. So here, the pump strength's just 25% of the inherent energy scale of the system. Here, it's 5 times the inherent energy scale, which ends up in a really big difference in rates when you're doing exponentials, right? So you can see that in all these cases, like, yeah, as the pump strength increases, you're pushed further away from the minimum possible state. But the pattern is remarkably constant throughout all of these. That in system size, in every case, there's at some point there's like a peak where it seems to be like uh, the nest is somewhat far away, you could say, from the minimum entropy state. But then as you increase system size, it goes and it decreases, and there's some kind of order of magnitude decrease there. So like if you look in this case, or this case, for example, let's do the highest case, so it's the most dramatic there. Here, for like at 80% pumps. So this is really, really strong pumps, and 80% of all possible transitions have a non-equilibrium pump. It's a very non-equilibrium system. However, as you increase the system size up to 20,000, what you find is that the NES, even in the most extreme out of equilibrium case we tested, is still only 10% above what the minimum entry production is. You know, um, so it's really quite a small effect that is decreasing with system size. It does seem to that it does converge at some point. It would be hard to tell without doing simulations that we don't have the hardware for, but there is definitely a behavior here that these big systems do seem to be minimizing. This nest is getting closer and closer to the maps. So normally this is where we conclude, but we have a couple of extra fun announcements for the first time. So this paper manuscript is called Large Interconnected Thermodynamic Systems Nearly Minimize Entropy Production. Maybe we can cross out the interconnected. So one of the common comments when talking about this is people will say, well, you had this big fully connected network, um, and there wasn't really like structure there, right? So you have this big structureless network, and you're maybe what's happening is what you've done, and this makes a lot of sense given what Alec was saying with like a permutation that keeps basically the entropy contribution the same. If each state has like hundreds of thousands of outgoing transitions and they're all sampled from the same distribution in a non-structured way, then it's kind of seems like there's some argument that these systems are getting more symmetric. Now, there is more going on than that because in these cases, it's not true that the NES is converging to uniform. So just to be clear, there is more than just that going on here, but it is something that's worth thinking about. So tried states that are sparse as well. So take a network and start pruning transitions to make a sparse network that's kind of has a more interesting structure as opposed to fully connected one. And here's a pump strength 1, and here's a higher pump strength. Again, the pump strength increases it. And as you go from blue to red, you're going to a dense to a sparse network. So again, the sparsity does seem to act like a non-equilibrium pump that pushes you away from the minimum, but still, as the system size increases, what you see is a consistent reduction in the distance from minimum. So it seems that in fact, even systems that are not super interconnected, in fact, these red lines are cases where I only kept 10% of all the possible transitions. So significantly sparser there. So this is early investigation. We haven't looked too much into this, but it does seem to be the case that the interconnected part is not necessary. Similarly, we can look at time symmetry. So this is slightly more interesting. When we talked about the environmental entropy production, right? We said it was like R of S to S prime over R of S prime to S. But of course, in reality, you need to time conjugate the reverse transition. So it's really like R of S prime dagger to S dagger. Now, typically people consider time even states a lot of the time, and that can describe a lot of systems, but it certainly is not everything. So if you allow for kind of arbitrary time symmetries to pair forward states and reverse states to kind of be involutions of each other, then you see the same kind of reduction as n gets bigger in terms of closeness to MEPS. But there is some interesting stuff happening here where this is a time even state. This looks like all the other things we've seen. It goes up, it goes down. The higher the pump strength is, the higher the further away you are from MEPS. Here you see the opposite. So there isn't the same kind of non-monotonic thing. And on top of that, it seems like low pump strengths actually have higher distances from equilibrium or from the minimum, which is which is really interesting. It seems like somehow there's more support, more efficient support for what we would think about as like non-equilibrium dynamics when you have these time-on systems. So this is a result that I think we'll be investigating more.
So just to summarize, left-hand side, time even, positional memory, which is a lot like most biochemical systems, right? Information stored in like DNA is time reversal symmetric. Information stored in biomolecule configurations is time symmetric. As you increase how non-equilibrium it is, it becomes less efficient. It's further away from min-ep as you progress from strength 1 to strength 5 on for the more complex systems, you're moving up on the graph. But for time odd systems where you're storing information and spin and momentum, um, as you increase the complexity of the system, suddenly the more non-equilibrium systems with larger pump strengths become more efficient than their uh, less driven counterparts. Am I phrasing this correctly?
No, I would say that is exactly what this hot off the press plot seems to be saying, which is maybe unintuitive and maybe not unintuitive, depending on what your opinion on time reversal symmetry is. There's definitely some very hand wavy argument that you can make, which is like something like momentum, which is a time odd variable. If you think about an equilibrium system, trying to drive something with a consistent momentum is quite dissipative, and so there's something there about maintaining a steady state might be in some kind of coordinates where that momentum is more natural, then you're able to kind of support um, a consistent loop, a consistent velocity at lower cost. Something like that is very vague at this point.
So you've done quite a bit of work in the idea of momentum computing, where you use sort of these time-odd degrees of freedom to make thermodynamic computing more efficient. What do you see as the connection between these results and what you've done there?
Yeah, I mean, I would love to have a good connection because I have like a deep intuition that they are connected. Uh, but I'm right now I would say it's a very fuzzy analogy that I don't think I can make a very strong claim of a good connection. But I would be curious. We have some real time symmetry experts here, so I'd be happy to hear what other people think.
Yeah, I think it's interesting. I it doesn't feel to me like I have a full story yet. I guess this points to a lot of experiments to do. Um, my like current way of trying to wrap my head around this is just like if I pump energy into a system with, say, momentum, then it doesn't need to dissipate that. Like it'll just the system will just go faster. And so that's not represented in dissipation. So maybe there's some like energy accumulation that's happening. but with spins, it's not clear what the analog is.
I feel like this was surprised me when I saw it, I'm not torn whether I should have been surprised or not about it.
Mhm.
But uh, I don't think it's obvious at this point what exactly is going on here. More experiment, we got to do more experiments, see how consistent this is, how real it is. There's other odd stuff going on in this graph, like the ordering is actually changing as the system size changes, which there is precedent for that. That happens here as well. There's intermediate regions where it changes. So could be that we're starting somewhere here, makes some kind of sense. But there's definitely the kind of the asymptotic behavior seems starkly different from what we found for kind of the cases with sparse networks and the cases with fully connected networks that have time even states.
Mhm. Yeah, I think well, the biggest question sitting with me right now is um, just like under what circumstances is it natural to be thinking of varying just the distribution or effectively like just the density matrix versus also the Hamiltonian, which is maybe a bit of like the Prigogine sort of thing. Although that was in a particular way. Um, I'm thinking of like if I don't know, you take me and you put me in a different room. uh, is that just changing the density matrix, or does it change the energies and so the Hamiltonian? It's a little confusing. I think it depends where you draw the boxes because like there's a way of describing things like in this universal light where like the Hamiltonian is fixed. But once you box a system into system and environment, then like you guys should correct me and iterate on this. But the my kind of recollection and understanding is that the effective Hamiltonian kind of depends on where you've drawn those boundaries. Does that seem right to you?
Yeah, it
The
does.
yeah.
I think the advantage of this sort of rate equation perspective is that it's sort of inclusive, or the density is inclusive of all dynamical elements. I think it's limited in that, you're only considering continuous time, uh, probabilistic non-Markovian dynamics. That in that way it's limited. But if you're imagining sort of that the say you include the driving source, the work reservoir as part of your system that's interacting with the thermal reservoir in tandem with your system, then I think it's reasonable to frame it this way, right? I'd connect it to, say, resource theoretic perspectives on thermodynamics, where, the battery is just a piece of the system.
Hmm.
Um, but I think the limit that your Markovian is important. I don't think that is sufficiently general to capture all behavior in the universe.
Yeah, I mean, I think it's a nice and important framework. It's unclear to me if like Markovianity is the same as the like I don't know limitation I'm talking about, but
The limitation of, having controlled work reservoirs. I mean, if we're talking about, having deterministic control of the system, one of the ways you can implement that is with a flywheel, right? That has sort of a nearly deterministic coupling, right?
Mhm.
Um, and I think this deterministic flywheel is going to be difficult to model with rate equations. So you could, have a model that includes the inertial flywheel and the system understudy together. But I don't think it's going to be a natural way to model it as a joint rate equation.
Mm.
I think the flywheel has effectively deterministic dynamics and as a result is producing if you encode that in rate equations, that means it's producing infinite entropy production, maybe. So maybe you need to store the momentum information about the flywheel in addition. I'm not sure. I haven't thought about it in detail, but I'd go to the flywheel example if you wanted to figure out how to express sort of the standard stochastic thermodynamic perspective in this rate equation framework.
I I do wonder about the fact that um, this whole framework, that all this every it's discrete states, right? The states are not continuous, and I think analogies that have momentum, like and stuff like flywheel, is like, what even is a discrete state flywheel? And it's kind of like the idea there is that it can like it it's only deterministic because it's like it can let off really, really tiny portions of itself, like of its energy. You know what I'm saying? I feel like there's some issue here about the state being discrete, which means like it can't like change its state by like a vanishing amount.
Mm. And
So
there's like a give and take in something continuous where you want to generalize rate equations to have like negative entries where you can have sines and cosines trading off against each other and making circular motion. So maybe some generalized version of that would better accommodate it. But at that point, there's all sorts of choices to be made.
Yeah.
I I think one of the things to think about in terms of what question we're really asking here and answering is, if you look at a system that's already in its steady state, it's in its steady state, it's producing some amount of entropy, and you ask the question, like, if it was in another state, would the entropy rate be higher or not? Like, and so what we're finding here is that almost always the entropy rate would be higher if the steady state was anything other than what it is.
Yeah.
Kind of a
Almost.
weird way of thinking about it, because the steady state just is what it is, which may be kind of what you're getting at, Paul, with like, you're kind of like, you put me in a different room. What does that really, is that does that really keep everything else the same?
Well, I think it's meaningful because it tells you what happens when you interact with the system briefly. It's like you suddenly change the configuration of the system, and maybe what you naturally expect is that the system will have some puff of extra heat and then relax back to its original state.
Right. Yeah, I'm curious. I'm curious if there's a situation like we haven't. This is something we're thinking about. Like, what if you perturb it to the minimum entropy state?
I think that's
Um,
hard to do. I think it's very rare that you knock into something and then it's like, ooh, I'm suddenly much more efficient.
yeah,
And
it should like never happen.
But
But what
time,
if we
but time does
surgically did it?
that.
sorry, what did you say, Paul?
But time does that. Time perturbs things to that state.
Not from the steady. Like, let's say you start in the steady state already.
Hmm. I
What
see.
what are
Yeah.
what are the odds that time perturbs you into a lower?
Oh, right. Yeah.
Yeah.
Very rare.
But they do exist. So let's say we did perturb into that. We haven't answered the question about, if you imagine the two cases where it stays steady state versus you instantaneously perturb from steady state to the minimum, and then see what happens as it returns, like over that interval. Is it true that going to the minimum entropy state transiently always induces some transient that will then overcompensate, and then in the end you end up dissipating more? Or would dissipating it to the minimum actually reduce entropy over that region? I'm not sure.
I saw you have some conclusions. I'd be interested in
Let's
that.
get in there. All right. So what do we say here? Fact or fiction? I would say fiction in the strict sense, but probably pretty much fact 100% of the time in any way that matters. Maybe my working hypothesis. So what we've observed is that systems tend to reduce the entropy production rate, but they're not minimizing it. So the steady state represents a reduction from almost every other state, but it's not a minimization. System size, as the system size increases, the distance between the NES and the MEPS in terms of entropy production seems to shrink for all the cases that we've tested. Uh, there's some hints here that EPR is playing a role in the organizational principle, but just saying that it's minimized is definitely not the whole story. So these results could be highly dependent on the kind of rate equations that are sampled. You already see some differences popping up, for example, when I introduce time odd variables. So one of the things that remains to be done here is just try different ways to sample rate equations and see how universal this is. So kind of always end by asking about what rate equations do other people care about that would be kind of interesting to test and just kind of solicit suggestions. So that will just wrap up with some funding acknowledgements, an acknowledgement of Alec, who's we've been working on this together, and that's that. Yeah.
Awesome. Thanks, Carl. Super interesting.
I think it would be a pretty cool superpower if when you bumped into something, it suddenly became more thermodynamically efficient instead of breaking it.
The Midas touch, Alec touch.
Yeah. The ray touch.
I feel like that's like a classic Midas touch situation that has unintended consequences.
Mhm.
Uh, can you explain one of the unintended consequences that you're imagining?
Well, I suppose I intuitively expect that the Midas touch actually is that, right?
Mhm.
Gold is very thermodynamically efficient.
Yeah. And so I guess if you would touch any living thing, you would instantly stop its life.
Ah, yeah, because it dissipates less entropy when it's not living.
Yeah.
Okay. That's too bad. I take it back. Let's not have that superpower.
Maybe just refine it. We need to refine it so that it somehow maintains its current goals. That's slippery slope. Superpowers can't be that fine-tuned.
Yeah, this is a monkey's paw situation.